Hello everybody and welcome back to On the Spot STEM. Today we will be doing 2019 F equals MA Exam B problem number 16. The problem reads, a hoop of radius r is launched to the right at an initial speed of v0 at ground level. As it is launched, it is also spun counterclockwise at angular velocity 3v0 over r. The coefficient of kinetic friction between the ground and the hoop is mu. How long does it take for the hoop to return to its starting position? For these problems, we always want to draw a free body diagram. So the first force that we'll draw is the gravitational force, or mg. The second force that we'll draw is the normal force, which is pointing directly up, and that's f of n. And since the hoop isn't accelerating in the y direction, f of n is equal to mg. And the last force would be the frictional force. Now we don't know what direction the frictional force is, so we'll look at the angular velocity to try to solve for that. Since the hoop is rotating counterclockwise, that means that the contact point between the hoop and the ground is moving to the right, which means that the frictional force which opposes motion would be towards the left. And we also know the magnitude of our frictional force because the frictional force is equal to mu times f of n. And since we mentioned earlier that f of n was equal to mg, we get the frictional force is equal to mu mg. Now if we define the positive direction as to the right, the frictional force would be equal to negative ma because the frictional force is acting to the left and it is the only force in the x direction that is acting on the hoop. So that means we can solve for a. Now doing the algebra, we eventually get a is equal to negative mu g, just by equating these two equations together. By kinematics, we can solve for the velocity of the hoop at any given time. So the velocity of the hoop is equal to v0 plus at. We want to use this velocity equation to figure out at what velocity will the hoop start rolling without slipping. So let's let that specific velocity be v of f. Now if we plug in a in this equation, we get v of f is equal to v0 minus mu gt. So this is the first equation that we need. Now the second equation we'll need would be relating angular velocity. So the first thing to note is that the current angular velocity, omega 0, is in the negative direction. Now to see why, since we define to the right as the positive direction, if the hoop was rolling without slipping to the right, that means that the angular velocity would be clockwise. And since right now the angular velocity is counterclockwise, it must be negative. So omega 0 right now is equal to negative 3v0 over r. Now we can use torques to figure out the angular acceleration of the hoop, which we can use to make an angular velocity equation. Now the torque is simply just the frictional force times the lever arm, which is r. And since the frictional force is equal to mu mg, this is equal to mu mgr. And since the torque is acting in the clockwise direction, the torque must be positive. So this is equal to I alpha. And we can solve for the angular velocity to get angular velocity is equal to mu mgr over I. Now we can use this to get the angular velocity equation. We get the final angular velocity is equal to the initial angular velocity plus alpha t. And since we know both the initial angular velocity and alpha, we can get omega f equals negative 3v0 over r plus mu mgr over I times t. Now since we defined Vf and omega f as the points where the hoop is rolling without slipping, we get the rolling without slipping condition Vf equals omega f times r. So to solve for v of f, we can multiply by r on both sides of this equation to get omega f times r, which is equal to v of f is equal to negative 3v0 plus mu mgr squared over I times t. Now remember, since this is a hoop, I is equal to mr squared. So we get v of f equals negative 3v0. If we plug in I, we eventually get mu gt. Now we can add these two equations together. Vf equals V0 minus mu gt and Vf equals negative 3V0 plus mu gt to cancel out the t, and we can use that to find Vf. So if we add them together, we eventually get 2Vf equals negative 2V0, which means that Vf is equal to negative V0. Now wait a second, since this is true, and the hoop was undergoing constant acceleration the entire time, the displacement of the hoop at this time would be 0. Now to see why, if we draw a VT graph, and if we let there be a constant acceleration with V0 at first and negative V0 at the end, we see that the areas on top and the areas at the bottom cancel out, which means that delta x is 0. So once the hoop starts rolling without slipping, it is already back at its starting position. So all we pretty much need to do is solve for t. Now we can use any of these equations to solve for t, but I'm going to use the first one. Vf equals V0 minus mu gt. So since Vf equals negative V0, we get negative V0 equals V0 minus mu gt. Now if we add V0 on both sides and add mu gt on both sides, we get 2V0 equals mu gt. Now if solving for t, we get t equals 2V0 over mu g. Now looking back at our answer choices, we see that this is in fact an answer choice, so we circle it and we're done. Thank you for watching. Make sure to like and subscribe for more videos and stay in tune for problem number 17.